All right. So, yeah, thanks for the introduction and thanks to the organizers for making sure this conference happened and inviting me. So, I'll be discussing some work that very recently just came onto the archive. It's joint work with Hendrik Weber, who's here, and then a PhD student of Hendrik, Guilherme Feltes, and both of them are at Munster. Okay. So I'll get started. So the story for today is global and time well-posedness for the generalized parabolic Anderson model, which is one of the prototypical or a kind of paradigmatic example of a multiplicative SPDE. So I'm going to be working in finite volume, so a d-dimensional torus. And here, I'm going to be dealing with the rough equation, and the roughness really enters in through a rough driving noise. So the noise zeta is going to have regularity -1 minus kappa for some kappa positive. And here I'm going to be using parabolic regularity, which you've seen in some of the earlier talks. And I'm going to allow sigma, well, I'm going to require it to be fairly nice. So for us, sigma is going to be something that is bounded with bounded first and second derivatives. Okay. So this is an example of a singular SPDE when kappa is taken to be positive. And just as a review, so I think we've seen power counting in some of the previous talks, but the idea is that if the noise is regularity -1 minus kappa, then Schauder estimate tells you that at best the solution would be 2 degrees better. So regularity 1 minus kappa. And if you plug that solution into a smooth function or a pretty nice function, you don't expect any more regularity. So sigma of u is regularity 1 minus kappa. And then if you try to go back to the right-hand side and define this product, the regularity exponents add up to something negative. So that tells you that you don't expect a canonical definition of the right-hand side of this equation in the same regularity class where you expect to find the solution. And so the kind of the way to make sense of this PD and the way that we're going to define our notion of solution is through the theory of regularity structures. So in particular, our solution theory depends not only on the noise, but an enhancement that is built from the noise, which I'll define a little bit later. And this local theory works for kappa positive, and it works all the way to kappa equals 1. And so here, so I should actually say, here I should change this to kappa. And kappa is greater than 1. The theory breaks down and so this is very similar to a power counting calculation you saw yesterday, that in that case, the solution is going to be of negative regularity. So, it's unclear how I make sense of sigma of u, but even worse, that tells me that sigma of u times the noise, I expect it to be worse than the noise. So here, when kappa goes beyond 1, I lose subcriticality. So this is a singular SPDE, but due to Martin's theory of regularity structures, we now, we have an understanding of the local theory for kappa between 0 and 1. So what do you mean by solution? Another way to think about what I'm calling a solution is a limit of solutions to regularized renormalized problems. So that is to say, I can introduce a regularization scale epsilon, use that to regularize the noise, and then solve an equation with a regularized noise, insert a renormalization counter term, which is the second term on the right-hand side, and then try to get a limit as I remove the regularization. And generically, we expect these renormalization constants to explode as we remove the regularization. So this is another way to think about what it is I'm talking about when I say solution. And so the theorem is that, so our global, well, our kind of crucial bound here is that if I assume, so I can't go as far as the local theory. So if I assume that kappa is, this is not exactly the optimal value, but a truncated decimal of it, of if I assume kappa is less than 0.132, then I have this bound on the solution between times 0 and 1, okay, where I have a constant that depends on like dimension, the regularity, and sigma, but then here I have the initial condition, and then some constant depending on my enhancement, which I'm using the symbol pi to represent. And so if I have bounds up to time 1, then by just restarting, I have global in time existence. Okay? So any questions so far? So here, this is L infinity. Yeah. Okay. So I just want to point out that we can treat a wide class of noises. So one class of noise we can treat is we can treat a Q Wiener process where our Q is given by this sort of operator. So this sort of power of the Laplacian. And so this is something that is, it's colored in space and it's white in time. And since it's white in time, it's been well studied. It's amenable to being studied using, Edo theory, and this was done by Deprato-Zabchik. But we can also deal with space white noise in dimension 2. And we can deal with more exotic situations. So we can take our driving noise to be, for instance, an imaginary Gaussian chaos. So Wick renormalized exponential of a log correlated field. Okay? And what I just want to say is, so this whole story is happening in a kind of pathwise picture. And one of the things that we see in this picture is that once we have the enhancement, we can kind of fix the enhancement. And the local and global analysis is fairly insensitive to the particular distribution of the law of the noise. Okay, so we have a clean separation between analysis and probability. Okay, and so here I just have a I have a slide of kind of previous results on kind of getting large-scale behavior of parabolic SPDE. So I'm sticking to the parabolic side of the world. But all of these results are somehow in a pathwise sense. So I don't want to, so maybe I won't go through all the work here. I'll just say that, so PAM was originally treated in Martin's original paper on regularity structures. And then Martin and Cyril also worked on PAM on the whole space. But it's as a linear equation, the global and time problem, at least in finite volume, is fairly, so there's less of a challenge there once the local theory is done. So phi4, as Hendrik described, you have this strong damping term. And so there's kind of been a lot of work on the global and time and space well-posedness of this equation, but the analysis of that equation is fundamentally, it's very different than for gPAM because this damping term allows you to kind of bound things a lot more brutally. And I'll just maybe, okay, so I'll just go to gPAM. So there's there is a kind of soft argument by Giuseppe, Peter, and Paul, using a comparison principle argument, constructing sub-solutions and super solutions using zeros of sigma. So there has been some past work on kind of global theory for gPAM, but so our work here is kind of requires a is more direct. So I want to kind of describe what the key challenge is here. And so the way that I describe why gPAM gives us so much difficulty is that the nonlinear behavior of sigma conspires with the spatial roughness of the noise and the solution. So those two things work together to make things very difficult. And so, for instance, if this equation in the smooth case, if you know that sigma is Lipschitz, then global existence is pretty easy, global existence in time. While if you don't have space, if you're looking at a rough ODE, then this has been looked at before in rough path theory. And in this case, with some work, you can show global, you can show global and time well-posedness with sufficiently many regularity assumptions on the nonlinearity here. Okay. So the difference for us is that we have roughness and we have spatial roughness. And to explain how that propagates through our analysis of the problem, I need to talk a little bit about the theory of regularity structures. So I'm going to talk about three major parts of the analytic theory of regularity structures, which is modeledness, reconstruction, and then integration of the Schauder estimate. So first I want to talk about modeledness. So the idea here is that modeledness is a way of thinking about regularity in a new way, where I'm allowing myself to approximate my solution with objects built out of the noise. So I'll imagine that if I say something is modeled, if I can approximate it locally with this sort of expansion, where the objects in green should be thought of as monomials. And so here there's a new kind of non-classical monomial, which is given by just the linear solution of the stochastic, the stochastic heat equation. So that's what this lollipop is. And in what follows, I'm going to use the regularity of this lollipop as my running parameter instead of kappa. So this alpha is going to just be 1 minus kappa. Good. So the idea is that even if U is classically not very regular, I can quantify its regularity with a better exponent if I allow myself monomials that are built from the noise. And so what I can do is I say something is modeled if I have some sort of jet that I can use to approximate it. So this capital UZW is this part of the jet with base point Z evaluated at W. And I say that something is modeled at level 2 alpha if I can use this, if I have such a jet that I can use to compare this guy's values at 2 points, up to this error estimate. Okay. And I just want to say that, so here, so I think Hendrik described these things as, well, the first one as a Gubinelli derivative, or and the second one, this kind of funny looking gradient, I'll call a regularity structures gradient. It turns out that if you say something is modeled and it has to actually solve your equation, then you get structural assumptions on these Gubinelli derivatives that appear. So this is related to what Hendrik was calling elementary differentials. And an argument where you freeze coefficients tells you that the thing multiplying the lollipop should be what multiplies the noise in the equation. And so the argument goes by so-called freezing of coefficients, which is that if I think that the right-hand side was too rough and I want to approximate it locally in order to deal with that roughness, then the natural thing to subtract here is sigma of u of z. So the sigma of u evaluated at the base point. And so through this sort of freezing procedure and trying to get good factors for modeledness on the right-hand side, I can actually iteratively calculate these Gubinelli derivatives. And they are elementary. They're an analog of elementary differentials. But this kind of, the regularity structures gradient is kind of an unknown. Okay, so I don't have, well, I mean, it's a little bit less explicit than this Gubinelli derivative. And so there's also a chain rule. So if u is modeled, so is sigma of u. And you know, the easiest way to kind of think about the chain rule is through compositions of Taylor expansion. So I can play the same game here, where in order to get the kind of green jet for sigma of u, what I do is I write sigma of u and then I insert the jet for little u. And I expand that and I drop terms of higher order. And so then I get the definition of this jet. Okay. Good. So the main problem I showed you on one of the first slides is that this product was ill-defined, this product on the right-hand side. And so how I can approach actually building that product is first think about it as a modeled object. And so sigma of u is modeled. The noise itself is modeled because it's perfectly kind of captured by the noise itself. And I can multiply those two jets, and then I'm led to this sort of modeledness jet for the product that I don't know how to define. And so here I've inserted a new monomial. And this new monomial is something that is not classically well defined. So this is really what we mean by the enhancement. So here, oops, and I think I made a small typo here. This should be W. Okay, well, but okay, so this thing is also some sort of increment, but fundamentally, you can think of it as a product of the lollipop and the noise. So it's a purely, it's an object that's a product of two Gaussians. So it's explicit, and constructing this object through probabilistic arguments is what we mean by saying that we've built an enhancement of the noise. And in practice, this is where you see the renormalization. So here, if I am defining this through a kind of regularization procedure, then what I would do is this is where I would subtract the renormalization constant in the definition of this monomial, and then you kind of see why I saw the counter term I saw before, because this is the monomial I'm shifting. And then this is the elementary differential that's appearing on the right-hand side, multiplying it, and that tells me what the form of the counter term is. Okay, good, all right. So the idea is I have a notion of the of a kind of jet for the product that I haven't as having difficulty defining. So now reconstruction is what allows you to actually build this product using the modeled description. And so for notation, I'm going to introduce this sort of parentheses L to just mean convolution with a scale L bump function centered about some point. So here this is, this represents a scale L average around some point W. And so the reconstruction theorem tells me that there is a way to define this product, and it satisfies this sort of bound that says that it's that's compatible with the kind of approximation of I have to it to the jet that represents its modeled expansion. Okay. And the key thing here is that the control of this product, it depends, so I need some information about the size of my noise, but I also use the modeled norm of sigma of u. Okay. So this gives me the right-hand side of the equation. And then to close the element, there's the Schauder theorem, which basically says that tells you that if you have the control of the right-hand side of this sort of equation, then you can capture the kind of regularizing by 2 in classical Schauder theory. And the way that you can think about it in this picture is that if you think about this freezing of coefficients equation, where here the kind of active variable for the heat equation is W, then you can get control on the modeledness of U based on some time scale based on having control of the right-hand side. And the kind of key point here that I just want to mention is that in order to control this right-hand side, this thing is very closely related to the difference I saw here in the reconstruction bound. So to actually apply the Schauder theory, I'm using the kind of reconstruction bound on the right-hand side, which is what allows me to make sense of this nonlinearity. Okay. Okay, so here, there's a little bit of a cheat here, which is I'm not using, the way to run this argument is to not use the kind of modeledness semi-norms that I introduced earlier, but to use a kind of variant that has a kind of blow-up condition near the time equals 0 hyperplane. But here, the kind of bound that you see is that you have control over the solution in 2 alpha. And then, I mean, the way to think about it is that the kind of last term is sort of a reconstruction term, okay? And the other 2 terms are related to things that differ between the reconstruction bound and what I put in the Schauder estimate. Okay. So the observation here is that if sigma of u equals u, then I can actually take this last term, and then for a small enough t, where the smallness does not depend on u. It actually just really depends on whatever combinatorial constants I have in the size of the noise. I can absorb this term onto the right-hand side. Sorry, the left-hand side. And I think I made a typo here. Sorry. Good. So, and so the fact that I can choose the smallest condition on my time doesn't depend on you is what sort of tells you that global in time existence is possible here. So this indicates that the global in time problem for the linear problem is much easier. Okay, but then if so if I have sigma of u genuinely nonlinear, then I need to control the modeled norm of sigma of u in terms of the modeled norm of u. And so this is where we begin to see the problem becoming really nonlinear. So because the chain rule is going to give us a nonlinear error term. So if I expand sigma of u of omega of w using the jet for u, then I get error terms that are quadratic in the jet. So you could say, okay, I'm going to allow you to make as many boundedness conditions on sigma as you want. Okay, that's great. So a lot of those coefficients that I see in u are going to be bounded, but I'm going to have this regularity structures gradient. Okay, no matter how nice I make sigma, if it's not linear, then I'm going to have to fight with that regularity structures gradient. Okay. So being careful, you can, if you kind of are, if you do this estimate a lot more carefully than this, you can get a pretty good interior regularity estimate. Oops, sorry, and I made a typo here. So you can estimate the kind of modulus of u in something that is linear, but on a time scale that actually depends on the size of u. Okay, so you can do the absorption that I showed before, but on potentially very short times that depend on the size of your solution. And so this gives us a kind of short time control. So what we want to do then is figure out how to get control on larger scales so that we can actually reach time one. So a time that actually doesn't depend on the size of u. And so the idea here is to look at a regularized equation. And so here UL just means I'm regularizing with this, this average of scale L. And what I can do is, so the thing is that this equation isn't quite closed, but what I can, so here the thing is that if I'm regularizing a product, that seems very different than working with the kind of regularized factors. But I can, in some sense, try to do a partial commutation of the regularization of the product and the regularization of the noise by kind of adding and subtracting terms. And I get an expansion like this, where this kind of term that I haven't written out is basically the left-hand side of my reconstruction bound. Good, sorry. Okay, so here I'm going to call it Isabel. And the main point here is that Isabel, so this, you can actually write out this thing fairly explicitly, and you can actually carefully extract its dependence on this regularity structures gradient. And then the second kind of important fact for this equation being tractable is that you can relate the regularity structures gradient with the gradient of the regularized solution with error terms that are tractable. And so then what you'll arrive at is you can rewrite the equation for the regularized solution in this sort of form, where you have some terms that have negative. So here you should think about L is less than 1. So it's something that I want to, there's going to be a kind of balancing of the averaging scale here. But I have one term that has negative powers of L, but allows for growth in U. And another one that has positive powers of L and no growth from U. And then there's the term that has the kind of superlinear behavior in the gradients. And so here I have this middle term where I have the gradient of UL multiplied by something that is allowed to grow in L. But what saves us here is that we've written this where this middle term here is a transport term, right? So if we're trying to estimate U sub L, then the transport term actually doesn't make it, the size of the transport term doesn't make a difference in that estimate. And so what how you can actually see this constraint on kappa up here is that you carefully balance the powers of L, well, the size of L, so that A sub L and C sub L are the same size. And then you see the bound that you get after doing this, and you require it to be sublinear in this in U. And if you do this, then it's this part of the analysis that you really run into this restriction on kappa. Okay, so I want to say that this this value of kappa that we have to be underneath, it doesn't have any sort of meaning in the local theory, right? So if you know the local theory of, if you're familiar with these sorts of equations, what you expect is that as the problem becomes more singular, you have to add more and more terms to your enhancement. But our expansion, our local expansion here is good enough for the local theory all the way up to a third. So this threshold doesn't clearly map on to any threshold that you see in the local theory. Okay, and I want to say some useful consequences of the global analysis is that so for this case of these the kind of Whiten time case, you have a global theory using Ito, but now this pathwise approach gives you allows you to actually construct stochastic flows, right? So there is a set of probability 1 where this dynamic continuously depends on my initial data, right? And that set of probability 1 doesn't depend on my initial data. So this strengthens the global picture for these equations in a nice way. And then I'll say that the case of imaginary Gaussian chaos is not just a kind of totally abstract choice, but it actually turns out that by looking at gPAM driven by imaginary chaoses, you can write down an argument that allows you to construct the massive sine-Gordon Euclidean quantum field theory. And so the fact that we have a mass is important for making this argument work, but the idea is it's a perturbation of a stochastic heat equation in 2 dimensions by a Wick-ordered sign nonlinearity. And then if you expand, if you do the the Prado-Debouche trick, if you expand about the solution to the linear stochastic heat equation, and you use trigonometric addition formulas or just facts about complex exponentials, then you can see that the remainder to the Prado-Debouche trick satisfies a gPAM system where basically the sigma is given by complex exponentials. Well, there are actually two sigmas and two noises. The sigmas are complex exponentials, and the noises are imaginary Gaussian chaoses. Okay, so the questions, so I mean, I guess two immediate questions are, can we go further into the subcritical regime? So, I mean, it's, I think we're still very far from having an understanding of how to do the full subcritical regime, but it would be nice to at least really understand how to go all the way to kind of the first threshold, where you need a new term in the local expansion. And then, of course, there's also the question of how to do things on the whole space. And so I think I'll end there. So thanks for listening.